to catch on all background.
So here's some stuff about photoluminescence. I try to keep it short and sweet because there's a lot of math and confusing parts behind this topic. So photoluminescence, and the definition of it is that when matter, how light absorbs or emits from it. So absorption is when matter takes in a photon and then an electron is moved from its initial state to a higher energy level. And then spontaneous emission is matter releases a photon from it, and then it drops an electron from a higher energy level to a lower energy level. And then stimulated emission, it's like just our spontaneous emission, but instead of it just happening on its own, we have to then introduce a photon to the system to then it will then drop an electron from a higher to a lower energy level. And we can see here that our photon is labeled as h nu, or h bar nu, where h bar is h over 2 pi, and nu is our frequency. And then in our last part, we can see that we have a photon going by it, and then we're emitting another photon. Something to notice about in the stimulated emission is that these two photons, they'll have the same direction as each other, frequency and polarization. And polarization is that it'll have that same wave in, I guess, the same direction to each other. So such that if like you were looking at them side by side, it would be looking like it was like you'd only see one because they'd be perfectly covering the one behind it. And then to Einstein coefficients, they measure how likely a photon will be absorbed or emitted from the atom, where A is our spontaneous emission from going from our level from X and Y. B, that can either represent the absorption or that should say the absorption or the stimulated emission, or spontaneous and X. Probability from our transition from X to Y. G of X is our degeneracy, which is how many states could be in one level, and then F of XY is our oscillator strength. And then we can see here that from our continuous spectrum, our emission lines, that's like where at a certain frequency we're going to get a photon out of it. We can see at those frequencies we're receiving light, which is what we can see. Then later on, then we can see what our absorption lines are. So when our photon absorbed, we're not getting any light back, so that's why we don't have anything. And that's what I have.
Okay, please join me in thanking you. We've got introduction to spectroscopy. Any questions to William in the audience? Any questions to William from online? Any questions in the chat line?
All right, I guess. So you have oscillator strength there. What would, well, I guess what's a good way to describe oscillator strength?
I'm not sure exactly what this oscillator strength is. My initial thought would be, since the light we're dealing with is a wave, would be some sort of strength of our photon or something related to that. My initial thought.
And what is your good memories of the talk by Joseph last time, or maybe 2 times ago?
that I'm not sure of.
Just ask him, maybe he will help.
Yeah, so the oscillator strength is related directly, like through these constants basically, to the probability that a photon will undergo that transition. So I guess from Will's equations here, we can see that there's like a few other constants that come into play, or a few other variables, I should say, like the frequency and the degeneracy. But like the main driver of it is the oscillator strength, which measures kind of like an overlap almost between two different like states. So if they have a high overlap, they have a high probability of transferring.
And
One thing that I would like to mention that confused me at first is that our E squared is the charge of an electron and not Euler's number squared. That's something that
Not what?
our E squared is the charge of an electron and not Euler's number, which confused me for a little bit.